All right. Hey, everybody. It is week 3, and this week we are talking about long-term agricultural research and soil sampling. So first things first is I want to start talking about land-grant universities. Now, land-grant universities are, for example, University of Missouri, and they're all public universities. And there's a couple in each state, but usually a flagship one. You would know a lot of them by name. But I want to give you a quick background on what land-grant universities are. So this is a map of the United States in 1859. You'll notice that lots of states aren't states yet. Hawaii is still a kingdom. Alaska is part of Russia. Anyways, so this is when the US is moving westward and they are running the Native Americans off all of this land here. And so there's suddenly lots of land in the possession of the US government, right? That they've pillaged and plundered here. And so they wanted to take that land and use it to invest in the citizens of the US. So one of the things that they did to invest in the citizenry was called the Morrill Act of 1862. It started in around 1859, working its way through Congress at the time. They had some other stuff going on, in case you didn't know. But anyways, what it did is it took 3,000 acres of this kind of pillaged land and gave 30,000 per member of Congress to each state to establish these universities in the public interest. So that would be 30,000 acres per member of Congress and per senator. So the kind of mission that they gave to them is they wanted to build universities for kind of working class, middle class people to obtain a more practical education in agriculture, military tactics, and engineering. And this is in addition to kind of the humanities, the classic liberal arts. Now, these universities were intended to be slightly different from the private universities at the time, the exclusive Ivy Leagues, which had a bunch of rich folks in them and stuff like that. They said, we're going to take government money and this newly stolen land and put that together as kind of a down payment to get these universities started. So they put those together, and we call those now 1862 land grants. So those are land grant universities from this initial Morrill Act of 1862. Now, in 1862, the US didn't consider Black people people. They weren't given full citizenship and rights and all that kind of stuff. We fought a war over it, all that kind of thing. But then after the Civil War, they said, well, we're going to keep universities segregated, but we still want to invest in them. So they have what's called 1890 land grants. So 1890 land grants are generally minority serving institutions, things like HBCUs, or historically Black colleges and universities, are generally 1890 land grants are generally HBCUs and that kind of thing. We have one actually down the road from us here in Missouri. In Jeff City, we have Lincoln University is a good example of HBCU that is also an 1890 land grant. There are also a smattering of other ones across the US. Then in 1994, they also added on another kind of category of land grants, and those are tribal colleges. So that's kind of the 3 categories of land grants. And these all have different funding mechanisms and whatnot from the US government. But they all have this similar mission, and they call it this tripartite mission. And so that mission is teaching, research, and extension. Now, when we're talking about long-term agricultural research, that generally falls within these latter 2, research and extension. Now, for those of you who don't know, extension is this system of like community agents and whatnot. They usually, sometimes at the county level, sometimes at the state level. But what they do is they're kind of public facing, and they do things like help with 4-H, or they do nutrition and that kind of stuff. But anyways, extension is public facing and public service oriented component of land grant universities, and it's a very important component. So long-term agricultural research, it helps fulfill those missions, but why would we want to do that, or why would we not want to? Now, of course, like anything, there are pros and cons. I'm going to start with the pros here of doing long-term agricultural research. So the first pro to doing it is that it takes a long time to see effects of land management. Sometimes it takes 5, 10, 25 years for a thing that you do on any given plot of land to make a huge difference. So when we have these long-term agricultural research experiments, we're able to say, no, this land is going to have this same research, so we can kind of wait that amount of time that it takes to see what any kind of management might have, the effects it might have. Another one is that when it's on university grounds, researchers have control over the day-to-day operations. They can there are staff and folks here who, will just plant it, harvest it, fertilize it, all those kinds of things that we need to do, and they'll put out these research plots, and that's a very unique skill to have. And so, we're lucky to have them out there and doing that for us, because I certainly don't have time to be going out and weeding and planting and all that in addition to my duties. So, this is a thing that as universities we have control over, and we have a funding mechanism for. Another thing is that when you're on a farm, there are so many different year-to-year fluctuations, whether it's just weather fluctuations and all the implications of that. Sometimes, you have more or less labor availability or time, maybe, you're pregnant or something like that, and so you can't harvest at a certain time. There are things like that, or you get sick, things like that. There are also kind of like market prices. If corn prices are high, you want to make sure you plant corn and not something else. So many things like that. As anyone who's ever been on a farm, things can be a little chaotic and uncertain sometimes. And so having long-term agricultural research sites helps us kind of not have to worry about that as much when we're doing these long-term projects. Another thing is that, there is a certain amount of little just nerddom in this. Like, it's a tradition, it's history. These are really cool things to keep going. And they are important, they're difficult, and they make research possible, and it's fun. So there's that. Of course, there are cons, there are downsides to this. So for example, we establish these plots, we establish these research trials, and we have some type of management. Now, that management that we set up, whether it's adding manure or different type of crops or whatever, those might not always be representative of what's happening in the real world. So, for example, 40 years ago, soybean was not a very common crop at all. But now it's obviously huge. It's one of the most widely grown crops in the US. So 40 years ago, we probably wouldn't have had a soybean trial, or maybe 50 years ago or what have you. But now, so if we had established the treatments then, they might not represent that. And we have these long-term treatments that aren't always representative of that real world considerations, I'll say. The other thing is that these are difficult and expensive to maintain. You need to have long-term funding, over decades to keep these things going. They're not cheap to run. Now here at Mizzou, we are fortunate enough to have 2 different long-term agricultural research experiments that have been going on. So the first one, and kind of the most commonly, the one that everyone knows the most, is called Sanborn Field. So here's a picture of Sanborn Field with some of the guys who helped get it off the ground. This guy right here, this fine looking fellow in the middle, is actually J.W. Sanborn, who the field is named after. Now, Sanborn Field was established in 1888, and it is the second oldest agricultural research site in the US. The only one that's older is just about 8 years older, and it is in Illinois, so just north of us here. But it's also the third oldest in the world. The oldest agricultural experiment is over in England. It's called Rothamsted. But other than that, Sanborn is towards the top, and it's pretty close to the other two. And when they set up Sanborn Field, they have a couple different questions and different rotations and stuff like that that they want to have there. So you can see here, one of the treatments is just crop rotations, corn and hay and all that kind of stuff. It's changed over time. Soybeans, for example, have gotten incorporated into it. But crop rotations was one of the main original questions here at Sanborn. Another one is manure. That was probably the main question that they wanted to have. They've added manure to some plots every year or every 2 years, for 130 years. So that's another of the main questions. And now there's also this other question of fertilizer. So nitrogen, phosphorus, potassium fertilizers are also added. So that's another kind of component that's out there currently. The other long-term agricultural research here at Mizzou are the Duley-Miller erosion plots. So these were started in 1917. You can see from this awful old grainy photograph. Interestingly, these started out as an undergrad research project. So, undergrads then and now are important drivers of research and research questions. And so back then, one of the undergrads said, like, what happens when we get these big rainstorms? What happens to topsoil and erosion? And, they didn't have a good answer for it. So they decided to set this thing up. And it's been going 100 years now, 100 years plus. And it's such a successful experiment, and they, were so impressed by it that they have set up maybe a dozen or so around the US similar to it now. And together those have been the basis for what's called the universal soil loss equation, which is how we predict erosion losses. We'll look at this a little bit later in the semester. Now, for those of you who want to get some extra credit, I will give 2 points of extra credit for anyone who can find where the Duley-Miller plots are. Go out there, just take a selfie next to the plaque or next to the field, and send that to me in my email by the 16th, and I'll give you 2 points extra credit on your next homework assignment. So I'm not going to mention it in class, so you're watching lecture, so you get those points if you can go out there and do it. Now, long-term agricultural research is clearly not just at Mizzou. Like I said, there's some at University of Illinois, there's some other places, but the USDA liked it so much that they set up their own long-term agricultural research network, or LTAR network, here in the US. And you can see that they have sites kind of all over the US. And each of these represents a certain kind of production context, and you can see watersheds and all that kind of thing. We have one here in Columbia, if it's kind of southeast side of town. That's the US, where the USDA ARS station is out there. So we do have one here. Columbia certainly has a lot of long-term agricultural research, that's for sure. And at each of these sites, they have crops or livestock or both. And most of them grow corn, but then they also have more like regionally appropriate crops. So for example, if you're down here in the South, you might have some rice here, or I know here in Eastern Washington, they're growing wine grapes, just things like that. Different places grow different crops, but they do have some commonalities among them. And they do have, so that way we can make inference, we can have research questions and understand what's going on kind of across the country through this long-term network. It's been around for about 15, 20 years now. Now, why do we want long-term research from a soil perspective? Well, it's because the soil remembers. That is, whenever something happens to soil, the signatures of it, the fingerprints, kind of stick around for a long time. And a couple years ago, we had a great illustration of this in England. So England in 2018 had some very extreme droughts. And there are a bunch of pictures like this that show up, and all of a sudden you see that these patterns show up. So this is, for example, a lawn that no one they hadn't seen this pattern before, but then when they went back and looked through some historical photographs and stuff, they could see that about 100 years earlier, when it was Victorian era, they set up these walkways and planters and everything that were there. You could see it's like almost a perfect match there in terms of the effect it had on the grass. And it only shows up when you're under this water stress. Now, I know you might be saying, well, that's 100 years ago. That's a long time. It's not super duper long. Well, there are other crazy examples. So this is one that was in southern England that year, and these are called cursus monuments. Now, cursus monuments are kind of ancient religious spiritual sites, and you can see them right here in this wheat field. You can see the outlines of them. Now, these cursus monuments were part of some religious ceremonies, and so old like druids and wizards and whatnot, just picture them kind of strolling along here. They would walk around it, and I don't know what they did in there. I'm not sure. But these are really, really old. And so archaeologists have looked at these, and they think that these date back to around 3500 BC. So almost 5,000 years ago, we can still see these fingerprints of what happened. They still show up under certain conditions. So I know you're thinking, because of course you're thinking, what does this mean for soil sampling, right? I know that's a thing that's on your mind. So here I am with the answers. This is another picture, again, from England in this drought. Other kind of old earthworks have showed up in this drought. So this is a wheat field. Just imagine that we're out in this wheat field and we want to take a soil sample, right? But it's not a drought year, so we don't know what's underneath it. So we go out and we're walking along this line of wheat, and we said, okay, well, let's just take a couple soil samples, and we end up taking it in these 3 different spots. Now, as you can see, those 3 different spots are very different, right? So here is super green and lush, here is pretty sparse, and here is kind of maybe middle of the road for it. And so if we took 3 different samples, those would be 3 very different results. And without this drought, we might not fully know why. So when we think through that, or when we are kind of taking that into consideration, we kind of start to think then about our sampling strategies when we go out and just take soil samples. Now, so let's say, for example, that we have a field, a site, maybe it's a forest, maybe it's a plot of land you just bought, maybe it's a wheat field, who knows? But we go out and we, let's say it's 20 acres, so it's a decent size here. And we say like, okay, we're just gonna kind of go for a walk and we're gonna do what's called random sampling. So as the name suggests, we go for a walk and we just start taking samples randomly around the property, right? Now, there are some definite advantages to going out and taking a sample like that. So for example, it's super easy to plan. We just kind of go out and go for a walk, and just kind of say, how about here? How about here? And then we also see that there's not that many samples to take. There's about 6 here in the whole field, right? So that these are some pretty clear advantages. But of course, there are downsides as well. So we're taking 6 samples and we're averaging that over 20 acres, which is a decent size. And so when we're averaging over that much, we're making a lot of assumptions about the representativeness of any sample that we've taken. So therefore, these samples that we got, whether intentionally or not, they might end up being biased. So just to give an example of what the biases might be, maybe there is a slight slope, for example. So let's say that, this is downhill slope here. And we can look at it, we go out to the site and we say, okay, well, we're going to do something called zone sampling then. So zone sampling, as the name implies, is we kind of section off the field into different zones that kind of to our eye look similar. So we could say, hey, here's the summit. And so we'll just kind of take some samples here. We'll group these samples together from the summit. And here's the slope here. And we'll say that that's another zone. And here at the bottom of the hill is a third zone, right? And so we could say we have zones A, B, and C, and we'll just take a couple samples from each, Now, clearly, that's still not a lot of work, right? But we are still capturing some of the variability. We're going out there and we're looking at it, and we are capturing to what to our eye looks like 3 different zones, right? Still, again, not very many samples. We only have 7 samples, for example, here. But the downside is that we are humans, we're imperfect, and we can't see everything. We can't know everything. So we might be actually choosing zones that don't capture the biggest effect on the thing that we're interested in. So say like plant growth, right? So continuing on in our field, let's say hypothetically, a couple years ago, something happened and someone was, say, doing a flyover and they accidentally sprayed something here that just makes plants grow like crazy, right? And similarly here, they accidentally sprayed something that makes them kind of grow worse. So what we end up getting is we get this, biased sampling that is not going the same direction. It's going perpendicular or the opposite direction to our zones that we made before. So how would we deal with this, right? How do we make sure that it's representative when we have both a slope and a kind of fertility or a plant productivity gradient? So there's another strategy just called grid sampling. So as the name implies, you put together this grid of regularly spaced lines over the course of your field, over the distribution of your field, and you go out and you take samples at the intersection of those lines. Now, there are some definite pros to this. So for example, these samples are doing an excellent job of capturing the field variability, right? We are evenly sampling throughout the field. And so we're getting a good sense of what's going on there. Now, very clearly, there are also some downsides, like this is so many samples. This is at least triple the amount of samples that we have in one of our other strategies, right? Similarly, the interpretation of our results from this is going to be a little bit more complicated. We don't necessarily know if any individual sample is representative. We kind of need to do the math on it is a little bit more complicated. I'll spare you the boring parts of it, but I'll just say the interpretation is a little bit more complicated when you do a grid sampling. So I know what you're saying. You're probably like, okay, so how can we even choose then, right? These all seem like they all have pros and cons and yada, yada, yada. So how do we choose? Well, a couple kind of guiding questions here. First off is, why are we going out and sampling? What is our purpose? Are we just trying to get a really rough sense of what's going on? Are we trying to diagnose a problem spot? Or are we trying to get like a really good baseline sampling before, doing some big project on it? So this, a good thing to know is, what is our purpose here? And kind of part of that is, how much previous knowledge do we have about that site? So for example, if we were going out to Sanborn, we have a pretty good idea of what's been going on there for the past 130 years. That's a lot of good previous knowledge. But if you just bought this property, for example, you might not have much knowledge at all. So you might want to have a better sampling to understand what's going on. And then there's also just this very practical, this real thing of how much time or money or expertise do we have to do these samples? Running 100 samples is great, but it takes some time, it costs money, and then you have to know what to do with those samples. So, these are all kind of considerations to have. So maybe to help guide that question, we want to know how many samples is actually enough, right? What is a good number of samples that we should shoot for? Now, remember, on our field, we have this fertility gradient. So towards the top, the plant, for example, is going to be growing slightly above the field average, right? And down here is going to be growing a little bit below average. And then, of course, there is the places that are exactly average, right? But we don't know what that average is until we get a good sense of the field. And the variation within the field is going to be a little bit random, right? And we want to make sure to account for that randomness. And the good thing about randomness is that, you know, there's a certain pattern here. So this is something called a Galton board, and these steel balls fall through and they hit these pegs and interact with one another, and they form this random, it's a bunch of random processes. But what you'll see is every time that it comes down, it forms this similar shape when it lands. So you see slowed down here, you can see all of these little bouncing, but every time it approximates this curve. Now, for people who have taken calculus, this is part of the central limit theorem, but sometimes we just call it the normal distribution, or the Gaussian distribution if you fancy. So when we apply this to soil sampling, right, when we look at our field, we say, yeah, there are going to be some points here that are below average, and some of the points that we take are going to also be above average. But what we're interested in is we're interested in the average representing the entire field, right? We can't go out and just take samples of every single spot on the field, though, unfortunately. But if we did, we would see that it kind of starts to, the distribution of the values approximates something like this, right? And so we call that the population distribution. There is a true average out there of the population. We might not always know it, but we are trying to approximate it with our sampling. So we want to make sure that we get enough samples to approximate that, that true average. Now, clearly, we can't just go out and take 2 samples. That might not be representative, right? If we take 2 samples and they both happen to be towards this end of the distribution, our average is going to be much lower than the real average. Similarly, if we take 2 from the top side, you know, might be here. But the frequency with which these observations occur kind of looks like this, and it gives you this average for the population. Now, if we were to adjust it for the number of samples, you see that if we take 5 samples, the distribution, we're more likely to get things that are further away from that true population average. This is the true average of the field. But if we're only taking 5 samples, we might end up a little bit below or a little bit above that. Now, if we increase the number of samples to 30 samples, say, for example, with that grid sampling, we have greater confidence. The range of values that we're going to get, the average of them is probably going to be closer to that population average. Now, this is what statistics does, is it is comparing these averages and the distribution, et cetera, et cetera. But so it's a good thing to keep in mind when we are out there taking samples, because this week you are going to be out at Sanborn. You're going to get a tour and you're going to do some soil sampling. You don't need to meet out there. We can just meet at 116 Abner, just like normal, and we will all go out there together. Now, like I said, we will be soil sampling, so make sure to dress accordingly. Right now, the weather looks like it's going to be okay. It might be a little wet, but we'll see. So because of that, wear shoes that you can get dirty, or that you're okay with messing up. If there's going to be rain, or if it's going to be cold or whatever, just make sure to dress according to the weather. Okay. Long sleeves are definitely preferred. Corn plants can cut you, things like that. If you do have a clipboard, just make sure that you bring one. We're not going to have anything really easy to write on out there. We have some for people, but if you have one, it'd be great if you could bring it. So I guess that is it for now. All right. Thanks, everybody.